All right, so let's start examining the multiple regression model and learn what we can do with it, what we can't do with it, how is it useful, etc. All right, so here is our multiple regression model. Basically, we have some quantity like GPA, sales, something that we want to predict that we use as the variable y. And we have a bunch of predictor variables, which we're going to call our x's. Specifically, we're going to let there be k different predictor variables, x1 all the way up to xk. And these are going to be characteristics of an individual, like height, income, IQ, the amount of money that they spend at Walmart, etc. So what the multiple regression model is actually saying is that someone's y value is essentially a weighted sum of their predictor variables plus a little bit of a disturbance. So remember, just like simple linear regression was relating the average value of y to x, a multiple regression model is relating the average value of y to the combination of x's here. An individual's value of y is going to deviate from the average by a random amount, and that's represented by the epsilon, the disturbance here, which we assume has a normal distribution, bell-shaped with a standard deviation of sigma. Sigma representing the typical deviation between the average value and the individual value here. All right, so the multiple regression model assumes that y is just a weighted average of the predictor variables. So how do we go about finding the coefficients, these betas here? Well, the betas really are going to be the unknown true values that we could only obtain if we were able to get data on every single individual in the population. But let's imagine that we have that, or imagine we just have a data set. How do we best estimate those coefficients? Well, once again, we're going to use the least squares criteria. So remember how the least squares criteria works? We're trying to minimize the sum of the squared errors, or some of the squared residuals. So remember, the residual is just the difference between the observed value of y and the value predicted from the regression. Or in other words, it's just the error made by the regression. And so the least squares criteria calculates the error that the regression makes for each individual in the data set based on the current set of coefficients, squares it, and then sums them up over all the individuals. And least squares criteria says, well, I'm going to pick the set of coefficients here that make the sum of squared errors the very smallest that it can possibly be. Now, it sounds like an impossible task, but actually finding these coefficients is extremely easy to do mathematically as long as you're a bit more familiar with advanced mathematic concepts like matrices, which we're not going to get into here. All the thing that we need to know is that these coefficients are found by minimizing the sum of the squared errors, the least squares criteria. Okay, once again, to differentiate between what the values are that we're measuring from our data and what the truth is, we have this beta versus lowercase b. So the coefficients in the model, the betas that we just talked about, those would represent the least squares coefficients if we had data on every single individual in the population. Those are the true coefficients. Now, since we only have a sample, we can guess what those coefficients are based on what the values are from least squares criteria on the sample. But to make the differentiation, we're going to call those estimated coefficients B0, B1, B2 instead of beta 0, beta 1, etc. So the coefficients that we get out from our sample are the point estimates of the betas. They're essentially our best guess of what they are, but we expect them to be off from the truth by a standard error or two. So we'll get more into that a bit later. Remember, the standard error typically just says, well, what's the expected difference between what we're measuring for something and what the true value is. So if I actually make a multiple regression model on a data set, this is the way that I'm going to write the equation. Basically, the estimated coefficients from least squares criteria are the lowercase b's because it's just a sample, and my predicted value of y is going to be a y with a hat over it. Okay, so before we actually get into interpreting what these coefficients mean and what multiple regression is really allowing us to do, we need to talk about what assumptions go behind this model, because there are a lot of them, and in order to use anything about the model, the assumptions behind it need to hold up. The model, in other words, needs to be an accurate reflection of reality to really get anything out of it. And the assumptions behind the regression model are ones that we've seen before, just with a few extra things going on. The first assumption, well, we said that the model says that the value of y is just a linear combination, or what we can call a weighted sum, of the predictor variables. And what that means is that the relationship between the average value of y and each predictor variable individually is linear. So if we look at scatter plots between y and x1, y and x2, etc., we should see linear relationships everywhere. Also, we should see equal vertical spread, basically the amount by which individuals differ from the average is pretty much about the same regardless of the characteristics of the individual. In simple linear regression, this meant that individuals were spread out from the regression line by about the same amount regardless of the value of x, and this is just the extension to when we have more predictors. Individuals typically deviate from the average by about the same amount everywhere we look. And finally, we also have the normality assumption that says, okay, yes, individuals are going to deviate from the average, but the possible deviations aren't just completely arbitrary. Rather, the distribution of deviations of individuals' values from the average is well described by that normal bell-shaped curve. And finally, and this is one that we haven't really gone into too much detail, if time is an explicit variable in the data set, so we actually measured it like the day of the week, or if it's implicit, in other words, the data was taken as a time sequence, so each sequential observation in the data represents, say, a new day, the next day in the series, then we need to make sure the residuals are independent from one another. And we'll talk more about that at the end of the semester. So here are our assumptions regarding the regression model. And even before really looking at any numbers with the multiple regression output, we want to make sure that the model looks to be adequate. Otherwise, none of the numbers even matter. It's a bad model. So how do we make sure that these assumptions look to hold up? Well, once again, we're going to look at the diagnostic plots of the multiple regression model. So, like we did with simple linear regression, we're going to look at the residuals plot, which is a plot of the residuals versus the predicted values from the regression. And we're also going to look at the histogram and QQ plot of the residuals. And with a multiple regression, we actually need to look at a whole new set of plots as well. We're going to have plots called the residual versus predictor plots. And what these are going to do, or these are going to plot the size of the residual versus each of the predictor variables themselves. So, for instance, if I was going to look at the diagnostic plots for the salary data set, if we're trying to predict salary from education and experience, this plot on the left is the residuals plot because it's plotting the size of the residual versus the predicted value of salary. Remember, we don't want to see anything interesting whatsoever here, no sort of curvature, no sort of unequal spread, and this looks fantastic. I'm happy with this. And we're also going to check the residual versus predictor plots, what the residuals look like versus education, and what the residuals look like versus experience. What I'm going to look for in these plots is any hints of curvature. If I see any curvature in the residual versus predictor plots, well, that means that there's not a linear relationship going on between the average value of y and that particular predictor. I'm going to need to employ maybe a transformation. So, all right, these diagnostic plots are used very similarly to simple linear regression. The way we check linearity is with the residuals plot, the residual versus predicted values, making sure there's no curvature, and by each of the residual versus predictor plots, making sure there's no curvature with any one of the individual predictors as well. If we're going to check equal vertical spread, we look at the residuals plot, just the plot of the residuals versus predictor values, and we should see more or less equal vertical scatter. Individuals shouldn't deviate from what's predicted by any more or any less based on the characteristics of that individual. So as you scan from left to right, make sure that the vertical spread going up and down is about the same. Remember, the horizontal density of the points can vary. The reason that this varies is just an artifact of what particular values of x the data happen to have. It doesn't have any sort of comment about whether or not regression is a good model. And then finally, we know we check normality with the histogram and QQ plot. The residuals, the distribution should look approximately normal here. So just like with simple linear regression, there are statistical tests to check these assumptions, and we're always going to start out by checking them first, but they only need to be passed if there's fewer than about 25 data points. Remember, for larger samples, these tests are relatively strict, And so if they do end up getting failed, and very often they do, what we're going to do is we're going to perform an eyeball check to make sure that whatever violations the tests are picking up on are small and inconsequential. Okay, more about the statistical tests. Remember, they're very strict with lots of data, and small violations are okay when we have more than about 25 data points. And the way these tests work is that they are passed when the p-value is 5% or bigger. So if all those tests are passed, then it's okay to use the model. You don't really even care what the residuals plots are. From a statistical point of view, it looks like the assumptions of the models are valid. If any of those assumptions are failed and you don't have much data, you need to stop. That model's not valid. It's not going to work out for describing how y and the predictor variables are related. If they are failed and you do have a fairly large data set, like we typically do in business analytics, we're always going to check those diagnostic plots. Small violations are okay, so only if we see any sort of obvious violations are we going to stop. If we don't see any obvious violations, it's going to be okay to use the model. Okay, so worst case scenario, we actually do see some sort of obvious violations. What do we actually do? Well, with simple linear regression, our strategy was to, instead of modeling the relationship between y and x, model the relationship between a transformation of y and a transformation of x, like log, square root of y versus x squared, etc. And we're going to do something similar here, but the transformation is going to depend on what type of violation that we see. So if there's curvature in the residuals plot, what we need to do is we need to see, well, what's responsible for that? We're going to look at the residual versus predictor plots, and depending on what these look like, it's going to change our strategy. So if there's only curvature in a few of those residual versus predictor plots, we're going to try transformations with only those x variables that show curvature. We might try predicting y from the logarithm of that predictor, the square of that predictor, etc. Only if there is curvature in all of them will we also try transformations of the y variable. So in a multiple regression context, when we see curvature in the residuals plot, that means there's some nonlinearity going on between y and at least one of those predictors. We'll check to see, okay, well, which predictor or predictors is responsible for this. If it's only one, okay, well, instead of predicting y from x, we'll predict it from some transformation of x. But if we see curvature in every single one of those predictor versus residuals plots, we'll also try transforming the y variable. All right, well, what if we see unequal vertical spread? What's our strategy? Well, the only thing that's going to help us out here is to try a transformation of y, like predicting the square root of y from our predictor variables. Transforming x does not help to correct the problem. Okay, so how do we get these plots out? Well, we've used this command already, check regression in R. Will give you the residuals plot, the QQ plot, the histogram, and then it will also show you all of the residual versus predictor plots as well. And so remember, if you see curvature in any of the residuals plots, this model is inadequate, can't be used here. And you'll look at those residual versus predictor plots, and for the ones that do show curvature, you may be able to fit a transformation. Instead of predicting y from x, predict it from maybe x squared or log x. You can play around with that. Okay, so let's just walk through an example here, our salary data set. We're trying to predict salary from education, experience, and months. So when we run check regression, we get the outputs of the statistical test first, and we'll always look at those first. And what we see for the linearity tests is that, okay, well, we're okay for education in months because those p-values are 5% or bigger, but we fail the linearity test for experience. So further investigation is required. We pass the test for equal spread, and we pass the test for normality. All right, so here's the graphical output, the residuals plot, histogram, and QQ plot, the first three by default, and then we follow that up by the residual versus predictor plots, one for education, experience, and months. And so we failed the linearity test with residuals versus experience, and so what we need to look at is to see if we see any obvious curvature. I see absolutely no curvature going on here whatsoever, so whatever violation that test picked up on is small, and we can ignore it. So it looks like it's going to be okay to use the model here. All right, well, what about the bulldozer data set? This is a Kaggle data set where we predict the selling price of a bulldozer based on a bunch of that bulldozer's characteristics. It's a pretty large data set, so the statistical tests of assumptions are going to be very sensitive, and let's just see what happens. So when I try to predict the sale price from all of the variables in the data set, that's what the twiddle dot does, I can check the regression. I have 5 different predictors, and it looks like, oh, I fail everything. All of the tests for linearity are failed for each different predictor variable, and the test for equal spread and the test for normality are all failed. Okay, it's a big data set. I kind of expected that. Let's see if those violations are big, or if they can be small enough to be ignored. All right, so our first 3 plots show the residuals plot, residuals versus predicted values, histogram, and QQ plot. And I see an obvious problem with the residuals plot. I see obvious curvature here, so there must be some nonlinear relationship going on between the sale price and at least one of my predictor variables. When I go into the residual versus predictor plots, the residuals versus sale date, residuals versus year made, etc., they all look pretty good except for this guy. The residual versus year made plot shows very obvious curvature, and in fact it looks a lot like the curvature we see in the residuals plot. So, okay, my assumption is violated. I can't use the model as is because there looks to be a nonlinear relationship between the sale price and the year made, so I need to go back and modify the model. Instead of predicting sale price from year made, I might want to predict it from year made squared, or the square root of year made, to see if that works. Okay, so predictor versus residual plots are a very useful tool. Let's just remind ourselves of how we work with the histograms and QQ plots of the residuals. These are used to check whether or not the residuals have an overall normal distribution, if the distribution of the deviations of individuals from the average is well described by a normal curve. And remember, what we're looking for is that the histogram needs to be roughly symmetric, and there's really quite a bit of leeway with respect to this. And the QQ plot should show a very specific type of pattern. Specifically, this dot should fall roughly on the diagonal line, and most of those points should be in between the upper and lower dotted bands. Typically, there's going to be some deviation at the far left and the far right. That's typical, and that's okay. What we're looking for is any sort of systematic, obvious, consistent curvature or bend to the points. So here's the QQ plot for the salary data, basically the expected size of the residual versus what we actually observe those residuals to be. And we see that the points are all essentially more or less inside the upper and lower dotted bands. Looks great. We can say those residuals are normal. Here's the QQ plot for the bulldozer data. So we already knew it's invalid because we have a nonlinear relationship going on between salary and year made. But we see this QQ plot is awful because while most of the points are inside the upper and lower dotted bands way out to the left and to the right, we do see a systematic weird bend going on where the points are not inside those upper and lower dotted bands. So normality is obviously violated here. No big news to us. We already knew that model wasn't going to be valid. Okay. So before even looking at any of the numbers, make sure your multiple regression model is a valid description of how the average value of y looks to be changing with your predictor variables. When you're assured and confident that it is a valid model, well, the coefficients can be interpreted. And now here's where the really tricky part comes, because the interpretation of the coefficients is probably the most incorrectly done task in a multiple regression context here. Most people end up getting it wrong. Even professionals do not interpret these coefficients correctly most of the time. So we want to make sure that you can actually do this. All right, first of all, the intercept beta 0 here is completely meaningless because that's basically the average value of y when each x is equal to 0. Why would you ever care about that? Well, you won't. Rather, it's the coefficient of each of those predictor variables, beta 1, beta 2, etc. So most textbooks interpret it in a particular way. I actually don't like that way because I feel it's a bit misleading and incomplete. So here is how we are going to interpret the coefficients in a multiple regression model. And this is about the most complete, specific, accurate way of interpreting what that coefficient means that I can come up with. So the way we're going to interpret the coefficient is we're going to say that two individuals that differ in xi by 1 unit, but whose other values of x are identical. So in other words, these two individuals differ in xi by 1 unit, but are otherwise identical here. Well, these two individuals are expected to differ in y by BI units. So whatever that coefficient is, that's what we expect their average value of y to be different by. If BI is positive, the individual with the larger value of xi is expected to have a larger value of y, etc. here. So what's nice is that in the multiple regression context, we're assuming when we interpret those coefficients that every single other predictor variable between these individuals is held constant, essentially. They're the same values. And so that way, when we look at that coefficient, it's basically giving you the marginal association between x and y after accounting for those other variables. So important interpretation here. We're never going to leave it like this because we always want to add context to the problem. We'll say what xi is, what unit is, what bi is, etc. here. So just as a reminder, remember that multiple regression is not a causal model. It doesn't establish cause and effect between y and any of our predictor variables. The only thing the coefficient is doing is it's telling us what the difference in the average value of y is between two individuals, or two groups here. Basically, what we assume is that the individuals in these two groups are identical, except for the values of xi for one group is 1 unit higher than the xi values in the other group. So what the coefficient is saying is that we expect the average value of y to be different between those two groups by BI units. That's all it's saying. It's only talking about the expected difference in average values here. So let's get practice interpreting the coefficient. The coefficient of education in a multiple regression model, let's say it's 13, and the other predictor we're using is education. So what this is telling us is it's saying, okay, well, let's imagine that we took all individuals with, say, 4 years of education and split them into two groups, say one with 9 years of experience and another with 10. So we have two groups of individuals. They differ in experience by 1 unit, 1 year here, but the values for their other predictors are identical. The values for their education are all the same, namely at 4 years. Well, if that's the case, this coefficient of 13 only means that the average salary for the group with 10 years of experience is going to be $13 higher than the average salary for the group with 9 years of experience. So that's all the coefficient is saying. It's just comparing the average value of y between two individuals or two groups whose xi value differs by 1 unit but who are otherwise identical. So just like with simple linear regression, the coefficient does not tell you anything about what would happen to an individual's value of y if his or her xi value increased by 1 unit, even if their other values of x stay constant. This would be a comment about cause and effect, and regression can never tell us about cause and effect statements. So what's one reason why? Well, remember, lurking variables can always be involved. We saw previously that if we fit a regression model predicting the number of body piercings from someone's height, it turns out that there's a statistically significant relationship. Obviously, it's not cause and effect. If you grow, say, an inch, that's not going to make the number of body piercings magically change. Rather, what's going on is that the association was induced by gender differences. Males are typically taller and have fewer piercings compared to girls. So really, that's why the relationship looks like it exists. It doesn't mean that if an individual grows a few inches, that's going to magically change the amount of body piercings they have. It's just comparing two groups of individuals. Okay, so practice with interpreting coefficients. One of the most important things that we're learning in this class. Here's our salary model predicting salary from education, experience, and months. Here's our output here where we're given the estimated coefficients along with the standard errors of those coefficients, how far off we think our estimated value might be from the truth, and also, we'll talk about this later, the p-values of those coefficients. So if I write out my regression equation, I say that the average salary is 2865 plus 93 times the number of years of education plus 12 times the number of years of experience plus 14 times the number of months they've worked at the company. All right, so what does this coefficient of 93 mean, the coefficient of education? Well, what this means, or what it implies, is that two individuals that differ in their educational values by 1 year, but who are identical in terms of their experience and their months, are expected to differ in their average salary by $93. Since it's positive, the person with more education is expected to have the higher salary. All right, what about the tips data set, predicting the tip percentage based on the bill amount and also the party size of the people at the table there? Well, here are the estimated coefficients for bill amount and for the party size with the standard errors and the p-values here. If I write out the regression equation, the tip percentage is equal to 19.9% minus 0.27 times bill amount plus 0.6 times the party size. All right, the coefficient of bill is minus 0.27. What does that mean? Well, that implies that two parties whose bill amounts differ by $1, but whose party sizes are identical, maybe 2, maybe 3, etc., they're expected to differ in their tip percentages by 0.27%. Since it's negative, the party with the higher bill is expected to have the lower tip percentage here. All right, one more example, and this was with a lot of variables. We've talked about the body fat data set where we try to predict someone's body fat percentage based on a lot of physical measurements. So here I'm fitting the model predicting body fat from all the variables in the data set, and here are all of the coefficients, the standard errors, the p-values, etc. And so let's focus in on the coefficient of abdomen. Here I've written out the corresponding regression equation. What does this 0.89 actually mean? Well, the units of abdomen and all these other guys are in centimeters. Body fat is in percentages. So what does this 0.89 mean? Well, what it means is that two individuals that differ in abdomen circumference by 1 centimeter, but who are otherwise identical, meaning they have the same age, same weight, same chest circumference, mid-arm circumference, all those other variables. Two individuals that differ in abdomen size by 1 centimeter, but who are otherwise identical, are expected to differ in their body fat percentages by 0.89%. Since it's positive, the person with the larger abdomen circumference is expected to have the larger body fat percentage. And so here is where we might sort of question the interpretation of this coefficient, because it seems rather unrealistic to really stumble upon two identical individuals with regard to age, weight, and every other physical measurement, but who happen to differ in abdomen circumference by 1 centimeter. Are there really two individuals out there? Well, maybe, maybe not, but that is what the interpretation of the coefficient is telling us. It's imagining two individuals who really are identical except in terms of their abdomen circumferences, and the coefficient tells you the expected difference in the y value between them. Okay, one more example with the body fat. We see that the coefficient of weight is minus 0.08. So what that means is that two individuals that differ in weight by 1 pound, but who are otherwise identical in terms of age, abdomen circumference, etc., are expected to differ in their body fat percentages by 0.08%. Since it's negative, the person with the larger weight is expected to have the lower body fat percentage. And now here's where multiple regression can seem to get a little bit weird, because the sign of this coefficient flies in the face of intuition, because intuitively it feels like we know that, okay, the heavier we are, probably the more body fat percentage that we actually have. So the fact that this is negative kind of doesn't sit well with us at first, but if we're very careful about the way we interpret the coefficient, there actually is kind of a rationale behind this, and it actually is telling us something interesting about the way the real world is working. So remember, when we interpret this coefficient, we assume that we're comparing two identical individuals, except for the variable of interest here. So the two individuals that we are comparing are identical in terms of age, abdomen circumference, chest circumference, etc. So basically these two people have the exact same physical dimensions and their age, except they differ in their weights. Now that's a little bit weird to find two people with the exact same physical dimensions and age, but weighing different amounts. But if those two people existed, really the only way that they could differ in weight is if the heavier person had more muscle. So muscle weighs more than fat. If you have the exact same physical dimensions, but you differ in weight, well, the heavier person is the one with more muscle. Well, and if you have more muscle, you're going to have a lower body fat percentage. So now, all of a sudden, that minus 0.08 actually makes a lot of sense. In fact, the data is recovering the way the real world is working. Two identical individuals that look exactly the same but differ in weights, the heavier person's going to have the lower body fat percentage because the heavier person's going to have more muscle mass. All right, so the overall lesson is that you need to be very cautious about how you interpret the coefficients of the model. The coefficient is very precise and you need to make sure to get it right. It is talking about the expected difference in y when we compare two individuals. These individuals are identical otherwise, or identical in every other regard except for xi. They differ in xi by 1 unit, and they're the same with regard to every other predictor in the model. Remember, this coefficient does not tell you what happens to an individual's value of y when their x value increases or gets smaller. And the result is that very often the coefficients in your multiple regression model may appear to be counterintuitive. They might have signs different from what you would expect. However, that's not an indication that the model is wrong. Rather, it's actually pointing out something interesting about the way the individuals in your data act. Basically, it's saying is that it says, hey, you know, the association between y and this x variable, after accounting for all the other variables in your model, you know, that may have an association that you just might not have expected. All right, one other thing about the coefficients of a multiple regression model is that they're actually model dependent. The coefficient of xi is going to depend on what other variables are included in the model. And this might drive you crazy because when you change your model, change what predictors are in the model and what's not in the model, the coefficient of xi is going to bounce all over the place. It's not going to be the same value when you change your model up. But this makes sense because remember the explanation or the interpretation of that coefficient is that two individuals that differ in x by 1 unit, but whose other values of x are identical, are expected to differ in y by b1 units or bi units. So if we change our model up and the other values of x are now different from model to model, well, it stands to reason that maybe the expected difference in y between them is also going to change. Depending on what we are accounting for and not accounting for, yeah, you know, the expected difference could vary quite a bit. So it turns out that the amount of change in the coefficient from model to model depends on how correlated your predictors are. If your predictor variables are weakly correlated, the value of the coefficient's not going to vary all that much. However, when the predictors are correlated, and when we have correlated predictors, that means essentially they share a lot of redundant information, the value of the coefficient from model to model can actually change dramatically and even sometimes counterintuitively between models. It does not mean the model is wrong. On the contrary, the data is yielding something that is relatively interesting and not obvious about the way your data is working. Okay, so let's just look at a few examples here. Back to our salary example, we saw that if we predicted salary just based on someone's experience, well, we saw that it was not a statistically significant regression. The p-value was bigger than 5%. So it looks like, no, you know, you don't do any better at predicting salary using experience than some random unrelated predictor. However, notice now that when we add in education into the model, the coefficient has changed from 10.4 up to 13.2, and now all of a sudden it's statistically significant. I'll talk more about that later. Remember, we saw that education was basically overshadowing the effect of experience, so after we account for education, the effect of experience becomes clear. But notice, look to just how much the coefficient of experience changed. All right, so this slide just kind of reaffirms what we were explaining there. What happens is that the people in the data set are varying in experience and education simultaneously. There's a bit of a correlation between experience and education. So some of the coefficient of experience in the simple linear regression, that 10.4, some of that coefficient is really due to education changing simultaneously. So after we account for the variation in y that's due to changing educational levels, we get a new coefficient out which better reflects how salary and experience are actually changing together. So some of this 10.4 was really due to education changing at the same time as experience does. Once we throw education into the model, now this gives a much more accurate reflection of how salary and experience are connected. All right, body fat. Well, notice that if we predict body fat percentage from someone's neck circumference, we have a positive coefficient like we would expect. The thicker the neck, probably the more fat that person is, the more body fat that person's carrying around. However, if we throw abdomen into that model, notice that the coefficient goes from positive to negative. And that seems a bit perplexing because we know that, okay, if we kind of eat a whole bunch, increase our body weight, our neck circumference is going to increase. So this sort of flies in the face of intuition, but what's the explanation here? Well, in a model by itself, the coefficient's positive, indicating that people with thicker necks tend to have more body fat. This is something we know. However, one thing about body fat percentage is that it also varies with a lot of other factors. It depends on someone's abdomen circumference, for instance. And to make things more complicated, well, unfortunately, someone's neck circumference and abdomen circumference change simultaneously. People with thicker necks also tend to have thicker abdomens. So, some of the difference in body fat percentage between two people with different neck sizes is probably due to them differing in abdomen sizes as well. When we look at this coefficient, this is talking about how the average body fat changes depending on someone's neck circumference. Some of this change is also due to abdomen because it's changing at the exact same time as well. So when we throw abdomen into the model, we account for the simultaneous change in abdomen size, and it turns out that once we do account for the variation in body fat percentage attributable to abdomen, the coefficient is now negative. Seems counterintuitive. Is it really? Well, once again, let's really focus on what the interpretation of this coefficient tells us. Remember, the coefficient is referring to the difference in group averages and not individuals' y values. So basically, what we're doing when we interpret the coefficient is we imagine two individuals or two groups of people who are identical in the other regards with respect to the variables in the model. In this case, they all have the same abdomen size, but the predictor variable of interest, the neck size, differs by 1 unit. Let's say one group has 38 centimeter circumference, the other one has 39 centimeter circumference. Here's the key insight. The negative coefficient implies the group with the larger neck circumference has the smaller body fat percentage. Now, I don't know exactly why that would be the case, but let's come up with the following theory. It could be the case that really the only way for people to have identical abdomen sizes but different neck circumference is if their necks are extremely muscular. Let's say they spend a lot of time working out their neck. And maybe that's just the way the body works. I don't know really how the body puts on fat or muscle, but maybe this is telling us something interesting about the way the body works. If you have the same abdomen size, but your neck circumference varies, maybe the only reason that can happen is that if the neck gets more muscular, in which case the overall body fat percentage is going to decrease. Okay, so interpretation of the multiple regression coefficient is extremely important, but as we have seen, it can be very tricky. The key thing is to remember that when we interpret the coefficient, we're basically looking at the difference in the average value of y between two individuals or two groups. These individuals look exactly the same. They're identical with regards to all the other variables in the model, except for xi itself, that predictor of interest. So two individuals that differ in xi by 1 unit, but who are otherwise identical, are expected to differ in y by bi units. So key interpretation, make sure you know how to do it. The next set of videos will go into evaluating the model to see if it is a good model or not so great.